It is very convenient to consider the diagrams in momentum space. And essentially, I will be interested in connected diagrams. And connected diagrams, essentially, these are diagrams such that if you start from any point on the diagram, then you can reach any other point on the diagram without breaking, say, your pen. So you can move over the lines of this diagram and reach any point on the diagram. So there are no disconnected pieces. Now, the point to consider only connected diagrams is dictated, or not dictated, but just by convenient, because actually you can generate all diagrams just from connected ones by a very simple procedure. Namely, it turns out that if you denote by W on J the generating functional for connected diagrams, so generating functional for connected diagrams, connected Feynman diagrams, then as a generating functional for all diagrams, no, without vacuum loops, I mean, is obtained from the one for connected diagrams by the following formula. Z on J is equal to exponential IW on J. So this means that if you know W on J, then you can compute Z on J by taking exponential. Another way around, if you know Z on J, then W on J is obtained as log, essentially as log of Z on J. Now, this relation between connected diagrams and all diagrams can be formally proven, and the proof is contained in my lecture notes. It's technical, so I'm not going to repeat it here. It's just would like to take this formula for the moment for granted, the simple relation between W and Z on J. And that's why having this formula means that we can completely shift our focus on considering just the generating functional for connected diagrams, and consider therefore only connected diagrams because they generate the whole set of diagrams. Now, in momentum space, the Green's functions are defined just by taking the standard Fourier transform. So Green's function depending on momenta P1 and so on Pm is defined as an integral Fourier integral. So dxi, you integrate I P1 x1 plus and so on I Pn xn, the Green's function g depending on n points x1 and so on xn. So this is definition of the Green's function in momentum space. Now let's look at the concrete examples, again using our scalar field. So for the 2-point function, say at leading order of perturbation theory, we have already established that the expression is the Feynman propagator x1 minus x2, and then there is Ig over 2 delta on 0 integral dz delta z minus x1 delta z minus x2 plus higher order terms. Let's take a Fourier transform of the term at order g. So at order g, we will have the following expression. So minus I, this is minus Ig over 2. This is all what is left over from Ig 4 factorial 12 delta on 0, and then there is this dz delta z minus x1 delta z minus x2. What I can do, I just substitute here explicit form of Feynman propagators as fourfold integrals. So this is integral over z here, over z. D for k divided by 2 pi to the power 4. I divided by k squared minus m squared plus I epsilon. I d for p divided 2 pi in the power 4. I divided by p squared minus m squared plus I epsilon. And then there is an exponential I k z minus x1 minus I k z minus x2. P minus x2. P z minus x2. So these are Feynman propagators substituted where their representation as a fourfold integrals. Now you see that what I can do is to perform integration over z. And integration over z tells me that I will be getting the delta function k plus p. And so one of the integrals, either over k or over p, whatever you prefer, you can take also with the help of this delta function. And so this means that what you get here is explicitly ig over 2 delta on 0, one integral left over, d for k divided by 2 pi in the power 4, exponential minus ik x1 minus x2 divided by k squared minus m squared plus I epsilon squared. So square appears because you have these two propagators, and since p is equal to minus k, say, then you see in the denominator, you just get k squared minus m squared plus I epsilon squared. Which means now that the Green's function g on x1 and x2 is given by first the Feynman propagator, which I also write where it's Fourier transform representation. So this is I exponential minus ik x1 minus x2 divided by k squared minus m squared plus I epsilon. And then this contribution, which we have just identified, g over 2 delta on 0, and I take I and put it inside the integral. Put it inside the integral. Which gives me the same exponent here, divided by k squared minus m squared plus I epsilon squared. So this is an expression which you will see at order g. And now you can take the Fourier transform of this expression. So Fourier transform means that you define g on P1, P2, and then according to the definition, you need to take a double integral over x's p1 x1 plus I p2 x2, and then you have first the Feynman propagator, just repeat the expression. This is what you get at leading order, and then at order g you have also one-fold integral where in the denominator you have now square. Okay. Now you see that you can actually perform integration over x1 and x2 without any problem. Say with respect to x1, it will give you delta function, which makes p1 equals to k. And another delta function comes out from integrating over x2. It will make p2 equals to k. So k, because of this delta function, must be simultaneously equal to p1 and p2, which means that integrating over x1 and x2 will leave you one delta function, which reflects the conservation of the momentum. So delta function, let me remind, is defined in this way. And this means that the connected Green's function in momentum space, g on x1, x2, g on p1, p2, is the following expression: 2 pi in the power 4 delta function p1 plus p2. As I said, there will be overall delta function reflecting the conservation of momentum. And then what will be left over is simply a function of a single variable, say p1, which will look, which we write like this. So first, there is a Feynman propagator at leading order p squared, p1 squared minus m squared plus I epsilon. And at the next order, there will be square of the propagator with a coefficient determined by delta on 0, which I write as I divided p1 squared minus m squared plus I epsilon. And then I write it in the following suggestive way for the future. Another propagator, p1 squared minus m squared plus I epsilon. So this is what you get for the Green's function in the momentum space, up to leading order in perturbation theory. Now, this term, which you get at order g, can be interpreted in the following way. So let's look at the following expression: 1 divided by k squared minus m squared plus I epsilon. And we end up in the propagator a small number, let's call it alpha. Let alpha be a small number. Then I can write this expression as follows. I can take out k squared minus m squared plus I epsilon. And then I will be left out with 1 minus alpha divided by k squared minus m squared plus I epsilon. And then using the fact that alpha is small, I can expand it as a geometric series and leave only the first term. So I will get 1 plus alpha divided by k squared minus m squared plus I epsilon, which, and I drop all high order terms in alpha. And so what I will be getting is k squared minus m squared plus I epsilon plus alpha divided by k squared minus m squared plus I epsilon squared. And this is exactly what I need. I see that the original denominator in the term proportional to alpha squares. That's exactly what you see here. This term squares, so you see it from this expression here. So this means that actually the Green's function, if you return back to the original expression, g on x1 and x2, using the smallness of g, assuming that you are working in perturbation theory, this can be written as follows: d for k, 2 pi in the power 4, I exponential minus ik x1 minus x2, and then in the denominator, you get this small alpha appearing in the form of the shift by g over 2 delta on 0 plus I epsilon. This is playing a role of small alpha. If you expand in this parameter alpha, then you will get at the next order exactly what you want, the square of the propagator. The square of the propagator. This is a very important observation, because it means that the pole of the propagator gets shifted. So pole, which originally was at the position m squared, now gets shifted by receiving an amount g over 2 delta on 0, which you can attribute as an appearance of small addition delta m squared due to interaction, due to the fact that you have an interacting theory, because this contribution is proportional to g. And this you may call the renormalized mass. A renormalized mass. So the effect of interaction leads to the shift of the position of the pole of the propagator in interacting theory to a new position due to the fact that m squared gets shifted by amount delta m squared equals to g over 2 propagator evaluated at 0. Now, up to this point, we have not asked a question about delta on 0. What is this? If you look at this quantity, delta on 0, then you see that this is the fourfold integral d for k, 2 pi in the power 4 I divided by k squared minus m squared plus I epsilon. So to compute delta on 0, you need to take this integral. This is a fourfold integral, but what is something which you see immediately is that this integral is actually divergent. So this integral does not exist. It is infinity. It's quadratically divergent because its numerator grows if you go, say, to spherical coordinate system, then the numerator grows like modulus of k in the power cube, so k cube, and the denominator grows like k squared. And so this means that this object behaves at large k as integral k dk, which is proportional to k squared. If you put, say, a cutoff, then it will be proportional to lambda squared, where lambda is the cutoff of this integral in the momentum space. So this object is actually quadratically divergent. And so we are at this point getting a quite paradoxical result. Although we assume that we are making expansion in the coupling constant, the quantity which is multiplied, this contribution at order g, is actually infinite. So in other words, what we see is that original mass, m squared, is renormalized by an infinite amount. But in fact, this is in accord with the basic idea of renormalization. So a physical quantity like a mass is not the same parameter as stands in the Lagrangian. So in the Lagrangian, originally we put some quantity which we call the mass squared, but we see that this m squared is getting shifted as a result of interaction. So it gets shifted by amount in the present case, g over 2 delta on 0. And in our case, this amount actually appears to be infinite. So the whole idea of renormalization, which is the next big subject in the quantum field theory, is to find a way to remove these divergences arising from Feynman integrals like this delta on zero at any given order of perturbation theory. Once again, remove all divergences at any given order of perturbation theory by performing the procedure of renormalization. I will leave it for the moment aside, the discussion of renormalization, and just note that the similar story, of course, holds for the case of the 4-point function and higher point functions as well, of course. So G on X1 and so on, G on P1 and so on Pn, being computed at, say, leading order of perturbation theory will be just an overall delta function, which reflects the conservation of momenta multiplied by the product of Feynman propagators in the momentum space, plus high order terms. This is how it will look like in momentum space. Now, self-energy and vertex functions. So, the mass of the particle, as we have seen, defined as the pole of the 2-point function, is not any longer a bare mass, as we call it. It's not just m squared, but it's m squared plus delta m squared. And what I would like to do now is to look at the problem of summing all orders of perturbation theory. And this is an idea of summing all orders. This is an idea which is directed to finding an exact Green's function. So Green's function to all orders in perturbation theory. Let me proceed with 5-4 theory. Now, as I already told you, we are mostly interested in connected Green's functions. And connected Green's functions, in a way, represent a first simplification, a first reduction, where from the general class of Feynman graphs, I reduce to a specific class which constitute connected Green's functions. And now I will make further reduction from the class of connected diagrams, connected Green's functions, to the class of the so-called one-particle irreducible diagrams. So one-particle irreducible graphs or diagrams, whatever you call them. One-particle irreducible graphs. They have a special name. They are called 1PI, one-particle irreducible graphs. Now, to define such one-particle irreducible graphs, I need first to construct the truncated Green's functions. And I already told you how to do this. So truncated Green's function is simply a Green's function from which I truncate the external propagators in the momentum space. So this means that I take an expression for the Green's function and I cut out the free propagators. The free propagators, I denote them G0, 2. The 2 means order, so propagator is just a propagator, so 2-point Green's function. 0 means it's a free theory. I take -1, so I invert this propagator and multiply the n-point Green's function. So this means cutting off external propagators, and I do it for all external particles. So one particle irreducible diagram is a connected diagram that cannot be made disconnected by cutting a single internal line. So once again, one particle irreducible graphs, these are graphs which cannot be made disconnected by cutting a single internal line in these truncated Green's functions. Now, let's have a look at the example which makes this concept very clear. So connected Green's function, say 2-point Green's function, is given by the following formula. So as we said, there is a free propagator. Again, I'm considering 5-Foss theory. Then at order G, there is this diagram, one connected diagram. External points are x1 and x2. And at order G squared, we will get the following diagram. So like this, plus there will be diagram like this. Again, two interaction vertices. And finally, there will be a diagram like this. 1, 2, 3. This is all at order G squared. And now let me, without proof, order G cubed. So you can see how it will go for G cubed. So I will get here 3. Here I can get these things like this. I can get things like this here and here. Propagator, there could be more things like this. Also 3 vertices, plus this. This is a cactus diagram, if you wish. Then there is a Mickey Mouse, like this. This is a collection of diagrams that you get at order G cube. Now you see, when you cut external propagators out of this diagram, then this is cut it out. This is external legs are cut out. No external legs. Let's cut out here external legs. They are truncated or amputed, as people say. And then you get these truncated Green's functions. And then you look at them, they're all connected. You see they're all connected. But what you see, for instance, is that there is a difference, say, between this graph here, between the first graph and second and the third. So in the first graph, I have an internal line, it's this line here, which I can cut out and make my graph disconnected. And then it becomes a sum of 2 disconnected pieces, while I cannot do it with graphs 2 and 3. Whatever internal line of graphs 2 and 3 I will delete, my graph will not become disconnected. Here at order G cube, it is a similar story. I can delete either this line or this line, and then the first graph becomes disconnected. Here I can also make this disconnected by dropping this line here. Here also, if I drop this one internal line, it becomes disconnected. This graph is connected, this is connected, and this is connected. In a sense, one particle irreducibility. I cannot delete a single internal line, making the corresponding graphs disconnected. And so these graphs here, 2 and 3, so one particle irreducible, this is also one particle irreducible. And here I see that this is one particle irreducible graph, this is one particle irreducible, and this is one particle irreducible. I hope the definition is clear, right?
Yes, yes.
Mm-hmm. Now, why this is important? What is an idea behind introducing this class of one particle irreducible diagrams. The idea behind is that if you have this, if you are able to sum up all these one particle irreducible graphs, then in fact you can build up through them all connected graphs. Again, this is like we are finding a more fundamental class, we are identifying, better to say, a more fundamental class of Feynman diagrams whose knowledge would allow us to reconstruct any diagram in the theory. Now, why it is so? Why these one particle irreducible graphs are so important? Now, if you sum all the graphs in this expansion, clearly what we get is a full two-point Green's function. And the two-point Green's function we can call a complete or dressed propagator. So it's a propagator, it's a Feynman propagator which is dressed by all possible interactions. So summing up all these graphs would mean that we are able to construct the full or dressed propagator. Now introduce the sum of all one particle irreducible graphs. So I call this sum of all one particle irreducible graphs by a proper self-energy. I give a term for this. So I call a sum of all one particle irreducible graphs. I call it proper self-energy. Proper self-energy. And I denote it by a letter 1 over I. So I is imaginary unit, sigma, depending on momentum P. Now, we see the following, that the complete propagator in the momentum space. By the way, what I'm doing also, I'm stripping away the delta function, which signifies the conservation of momentum. So delta P1 plus P2, I'm not considering it. I'm just assume that it exists as an overall coefficient, and I'm not interested in it. Then I know that all the graphs which I have here depend just on the one variable. And this variable is P1, which I denote by P. Yeah, so this is one variable on which everything depends. Then my Green's function, G2, which is complete propagator, starts from G0. So I say G complete two-point function start from the free two-point Green's function G0 on P, and G0 on P is just the usual Feynman propagator, P squared minus M squared, like this. And then what I can have? I can have one propagator, G0P, self-energy divided by E, and then G0 on P. So this contribution which I have here would correspond, for instance, to this graph here. You see, this G0 and G0 will restore the imputed propagators, free propagators, and then contribution from one pi, this would be a contribution to this self-energy. Analogously, this one pi, I restore these propagators, and then I get a contribution to one pi from these graphs. But there will be more complicated combinations where I can have not one particle irreducible graphs, which has a structure sigma on pi, then again free propagator, then again sigma on pi, and then again free propagator. This would correspond, for instance, this kind of graphs, right? So it contains this restores one external propagator, G0P, another external propagator, another G0P, then there is a propagator in between, this guy, and then contribution coming from one particle irreducible sum of all one particle irreducible graphs. But then it's clear that you can continue this. You can continue this game, so you can have G0 P sigma on P over I, G0 on P, sigma on P over I, again G0 on P, sigma on P over I, and so on. Right? Up
Professor,
to infinity.
Can you explain the rule again?
The rule is very simple. Again, what I'm doing here, I'm just restoring back in the whole sum of Feynman graphs. I'm restoring back external propagators. This is this external G0P from the left and from the right. G0P from the left and from the right. And then these propagators inside, in between this sigma on P, these are propagators which makes my graphs not one particle irreducible. So deleting one such propagator makes this graph not to be one particle irreducible, right? So basically, what is written down here is a restoration of the full class of connected Feynman diagrams from one particle irreducible ones. This is what it is. And this restoration is an infinite series. It's done in the form of one distinguished quantity, which is called proper self-energy. And proper self-energy is a sum of all one particle irreducible diagrams. So those diagrams which cannot be made disconnected by removing a single internal line. And so the difference between all the connected graphs and one particle irreducible graphs are precisely those graphs which are not one particle irreducible. So those graphs which can be made disconnected by deleting just a single line, single internal line. And now this procedure which I'm following here, that's basically reconstructs all these diagrams which are not one particle irreducible by putting these free propagators in between a proper self-energy. Okay, so this is what I'm doing here. I'm restoring the full class of connected graphs from one particle irreducible graphs. And proper self-energy is the sum of one particle irreducible graphs at any order of perturbation theory. So at any order of perturbation theory, there is, of course, a finite class of all such one particle irreducible graphs. But if you sum up to all orders on perturbation theory, then this is an infinite quantity because it contains an infinite class of such one particle irreducible diagrams.
Sir, but what does it mean physically? Why are we doing this? It's mathematics. It's a rule.
Why we are doing this?
Yes, physically.
That's exactly what you will see in a moment. Because that series you can sum up in a very easy way. So you take away G0 on P on the momentum, and then you have 1 plus sigma on P divided by I, G0 on P plus sigma on P over I, G0 on P, sigma on P over I, G0 on P, and then you see what you get. So at n soda, you will get something like sigma on P over I, G0 on P in the power n, right? And so on. Which tells you that what you have in the brackets is a geometric series, which you can elementary sum up. So you get G0 on P, and here 1 minus No, maybe I should write it like, I should write it in this way for simplicity. 1 divided by 1 minus sigma on p divided by I, d0 on p. And if I take d0 on p out to cancel it with what you have in front, then you will get 1 divided by g0 on p in the power minus 1. Perhaps I will write here. And let's see. Here I will also will have I, right? And sigma on p. And now I remember that the inverse propagator, so g0 on p, is I divided by p squared minus m squared plus I epsilon. And if I invert it, I will get I divided by I p squared minus m squared plus I epsilon divided by I. So I cancelled, minus sigma on p. So this shows me that the full propagator, which is the sum of all connected Feynman diagrams, is given by the following expression: I divided by p squared minus m squared minus sigma on p plus I epsilon. So what do you see from this expression? You see that actually the pole of the propagator, of the full propagator, gets shifted by the amount which comes as a sum of all one particle irreducible graphs. In other words, a proper self-energy. It's called self-energy because its origin due to the self-interaction of the phi-4 theory. It's a quantity which depends on the Kaplan constant, and it arises because of non-trivial interactions. That's why it's called self-energy. And we see exactly the effect which we have seen at leading order of perturbation theory, the shift of the mass. This time it's a more complicated effect because shift happens by a quantity which is itself a momentum dependent quantity. Yeah, so sigma on p is a momentum dependent. And we understand due to what this happens. This happens due to the sum of all one particle irreducible Feynman diagrams. This quantity shift the pole. Now, if I want to store the full Green's function, so complete Green's function, as a function of P1 and P2, what I need is to return back my four-dimensional delta function, P1 plus P2, and then it should be multiplied by this quantity G2 on P. Then it would be complete Green's function in this theory.
But
now, yeah.
Sure, but I think, shouldn't we remove sigma p by some way?
How we can remove it? I mean,
Because
it is there. It's a sum of all one particle irreducible graphs.
But this also leads to infinity.
That's another question. The way how we remove it, we cannot remove it, but we can renormalize. And as I said, renormalization in this context would mean to make this Green's function G2 to be finite at any order of perturbation theory. That's what we can do. Actually, that is what we should do if we want to give a meaning to the quantum field theory. But for the moment, we don't know. We just say, okay, if we play this game of the perturbation theory and just sum up all the graphs, then we see that the complete propagator, which is this G2, depending on P function, gets a contribution to its free part, to the usual Feynman propagator part, by the self-energy, which represents the sum of all one-particle irreducible graphs. That is our conclusion at this point. We also see the following, that we can introduce a quantity which is called vertex function. If we rewrite this formula here as G2 on P multiplied by P squared minus M squared minus sigma on P plus I epsilon. So I epsilon, let me drop it. It's not so important in the present discussion. Then this is G2 on P multiplied by gamma on P, gamma 2 on P. And this is equal to I. So this I will be left over on the right-hand side, which actually, allows me to introduce a quantity gamma 2 on P called vertex function. Vertex function. Gamma 2 on P, depending on one variable in this context. And this is simply an inverse propagator, inverse Feynman propagator. No, up to this I, it's an inverse Feynman propagator, but Feynman propagator, how to say, corrected by self-energy. So inverse Feynman propagator, inverse free propagator, and on the top, there is a contribution of all one-particle irreducible graphs. This is called a vertex function. And the vertex function is an important new quantity. In fact, we can introduce an infinite number of vertex functions by making them in a way equivalent to Green's functions through the so-called Legendre transform. Legendre transform is something which you know very well from classical mechanics. Legendre transform, which works in this way. So I consider the W on J as a generating functional for connected Green's functions. And on the top, I introduce the generating functional for vertex functions. This is gamma, depending as a functional on field phi. And I have to add a term which couples my classical source G on X with another classical field which I denote by phi on X. So phi on X is not a quantum field; it's a classical field, and this relationship between W and gamma reminds you the standard Legendre transform which you get in classical mechanics, where you relate by means of this transform the Lagrangian as a function of Q and Q dot to the Hamiltonian, which is a function of canonical coordinates and momenta. And the relation between them is due to this formula, as you know very well. Lagrangian function of QQ dot is PQ dot minus H depending on P and Q. And something similar is here. So you introduce a functional gamma on phi by means of this Legendre transform, from where you see that if you take a variation of W on J over J on X, where in the right-hand side and treating phi and J as independent variables, you will get phi. So it defines you phi as a functional of J, or you can use it to compute J as a functional of phi from this formula. And analogously, d gamma on phi over phi will give you minus J on X. So these formulas are transition formulas, which allows you to compute gamma on phi if you know W on J, or we can compute phi via J or J via phi by using these formulas. And therefore, if you know one of these functionals, either W or gamma, you can restore another one. Now, how this is connected to this quantity gamma 2, which we have introduced? Let's see. Let's consider the full 2-point Green's function, J dependent on x1 and x2. We know that this is 1 over I. Second variational derivative of W with respect to the source J. Now, if you substitute the variational derivative dw over dj as phi, then we get from this formula that this is minus I delta phi on x1 divided by delta j on x2. Now what we can do, we define a kernel gamma depending on x1 and x2. Quite analogously to definition of the Green's function, namely as a second variational derivative of gamma with respect to this field phi, like this, okay? And then we see that this is, according to the formula coming from the Legendre transform, delta j on x1 divided by delta phi on x2. And finally, if I now integrate over z, g on x1, comma z, gamma z on x2, and substitute these findings into this formula, what I will get is, let's see, I integral dz and delta phi on x1 and x2 is z, so delta j on z, multiplied by now for gamma x1 becomes z, so delta j on z, delta phi on x2. An integral runs over z, and so you see what is written down here is simply I delta phi on x1 over delta phi on x2. But this is nothing else as a delta function, right? x1 minus x2. So in other words, we see from this computation that the 2-point Green's function and this kernel gamma, which we have introduced as a second variational derivative of the functional gamma over the field phi, these two kernels is simply inverse of each other. So gamma is an inverse of G. And if you now substitute for these gammas, for this G and gamma, their expression in the Fourier space. So what I mean is that we know that this is gamma on x1, x2 can be obtained as a inverse of the Green's function in the momentum space. So Fourier inverse of the Green's function in the momentum space, which is x1 p1 plus x2 p2. And then we substitute the Green's function in momentum space, which we know that it contains this delta function on p1 plus p2, and then gc on p, say on p1. Then integrating out one of these delta functions, we will be left over with one integral exponential minus ip x1 minus x2 gc on p2, like this. C means connected. C means simply connected. Okay, so this is how our function depending on two variables in the X space is connected to the expression depending on being the function of one variable in the momentum space. Analogously, for gamma, we assume the same structure. So gamma on x1, x2 is dp over 2 pi in the power 4 exponential minus ip x1 minus x2, and then there is a function gamma 2 depending on p. Now, if we take these expressions and substitute the right-hand sides into this formula and integrate, so we get the following: integral dv dc x1 comma z gamma z x2 equals to integral dp 2 pi in the power 4, and then there will be exponential minus ip x1 minus x2. So we have to substitute. We will have two integrals over momenta, but then the integral over z will produce one delta function, which allows to take explicitly one momentum integral, and will be left over with just a single momentum integral. So exponential minus ip x1 minus x2. And here you will see the product gamma 2 cp, gamma 2 p. And we know that this is equal to I multiplied by delta function. And if I write delta function in the momentum space, then this is I dp over 2 pi in the power 4 exponential minus ip x1 minus x2. And so comparing the left-hand side with the right-hand side tells me that from here I deduce exactly the desired relation between G and gamma in the momentum space, which we have just seen from our introduced definition of gamma. So originally my derivation started from the introduction of self-energy, so one particle reducible graphs, and then I said that this formula which we got makes convenient to introduce the quantity gamma 2, which is related to the propagator, to the full propagator or dressed propagator by means of this formula. And now we see that this quantity gamma 2 is nothing else as generated as a momentum space kernel of gamma x1, x2 coming out as a second derivative of the functional gamma with respect to the field phi. Okay, so that's exactly the formula, expected formula I wanted to obtain. This is not the end of the story. In fact, if we look at this formula, where is it? At this formula here, so saying that gamma integral of gamma of gc on x1 comma z gamma z x2 is equal to minus I delta function x1 x2 x1 minus x2. And if I substitute here the expressions of g and gamma via their variational derivatives of the corresponding functionals, then I get the following expression. Then I get the following formula: integral over z, second variational derivative of w, delta j on z, second variational derivative of gamma, So this is functional of j and this is functional of phi over delta phi on z, delta phi on z prime. So external variables for me is convenient now to take x2 and z prime. And on the right-hand side, I will get minus delta function, x2 minus z prime, and I disappeared because the definition of GC contains I. So this I disappeared, and then I get this minus delta function. So now we look at this relation, and we do the following. Let us apply to both sides of this relation the variational derivative, delta delta j on x. This variational derivative can be written where the Green's function in the following way. I can do the following. I can first differentiate over z, differentiate over phi over jx, and then differentiate over phi on z. But this is nothing as a Green's function. So this is phi over j. Where is it? Phi over j. You see up to I, this is my Green's function. And so I can write it as I integral Green's function, full Green's function, GC connected, Zx, dz here, delta phi on z. And why this is useful? That's because now I would like to take this variational derivative and act on both sides of this relation. So on the left-hand side, I will get dz third variational derivative of w. With respect, I will be acting, so x I make x1, delta j x2, delta j z. Second variational derivative of gamma is not changed. It's what it is. Plus, by Leibniz rule, I have now to take this variational derivative and acts on second variational derivative of gamma. But then I will act by using this formula because that replaces variation over j by variation over phi, which is convenient for me. And so I will get another integral, dz. Here, nothing would change. While here, I will get what I will get is I g dz, no, dz, let's write dw, and then g c z w, delta phi on w, applied, there would be now second gamma on phi, delta phi on z, delta phi on z prime. Okay, and this is equal to 0 because on the right hand side there is just a function which does not depend neither on which does depend neither on phi nor on j. Therefore, the result will be 0. So I'll get this functional relation. But then we see that in this functional relation, I can write it in the following way. So on the left-hand side, I have third derivative, dz third derivative, delta j x1, delta j x2, delta j z. This second variational derivative is nothing else as kernel gamma on z prime minus I, and here I substitute, so dz d omega, let me, omega makes Let me make it just double prime, z double prime. So I write it as a dz double prime. And then there will be integral. So original integral was over dz. Now there appears an integral over dz double prime. And here I will write this expression here also as g, depending gc depending on x2 z, right? There is another gc depending on z double prime. And let's see, x2z, z double prime, z double prime. I make j to be x1. Sorry, here must be x1, and here must be w, like this. So x1 is there, and here there is a third derivative of gamma on phi, differentiated over w is now z prime. So I first write z, then I write z double prime, and then I write phi on z prime. And this is all equals to 0. And the final step consists in inverting this relation, how I can multiply both sides of this formula by gc full propagator dependent on z prime and x3. x3 is an external point, and integrate over z prime. And so when this gamma meets this gc with an integration over z prime, I know that it will produce for me delta function which replaces the point z by x3. So on the left-hand side, in fact, I will be getting delta 3 w on j over delta j on x1, delta j on x2, and delta j on x2, delta j on x3, right? This is what I will get on the left-hand side. And on the right-hand side, what do we get on the right-hand side? On the right-hand side, I multiply the whole expression by one more Green's function depending on z prime x3. And so there will be now on the right-hand side a triple integral. So z prime and z double prime, I can now denote as a delta z1, delta z2, delta z3 for the symmetry. And then gc depending on x1, z1, gc x2, z2, gc x3, z3. Okay, so 3 full propagators cross the third variational derivative of gamma with respect to the field phi. This is what is very natural to denote as gamma 3. Gamma 3 depending on z1, z2, z3. And this means that on the left-hand side, the expression on the left-hand side, this derivative here, is nothing else as a connected, by definition, is a connected Green's function depending on x1, x2, x3. So this is Green's function gc depending on x1, x2, x3. And on the right-hand side, divided by I, we will get 1 over I. Integral dz1, dz2, dz3. Full propagators, or rest propagators, z2, gc, x3, z3, multiplied by the vertex function gamma 3 on z1, z2, z3. Now this formula can be inverted by multiplying with gammas 3 times, gamma, say, on x1, gamma x2, gamma x3, and integrating over x1, x2, x3, this formula can be inverted. So you can restore back the vertex function gamma 3. So this is gamma 3 connected green function, and this is gamma 3 vertex function. It can be restored back via connected Green's function in this way: dz1, dz2, dz3, gamma z1 x1, gamma x2, gamma z2 x2, gamma x3 z3 x3 multiplied by g3 connected z1 z2 z3. So these are the formulas which allow you to move between the Green's functions and vertex functions, which makes them, in a sense, equivalent. If you know Green's functions, you can reconstruct vertex functions. And if you know vertex functions, you reconstruct Green's functions. So in fact, you can see also that this gamma on phi, the full generating functional, for these vertex functions is nothing else as the following sum. So sum from 0 to infinity, 1 divided by n factorial, integral dx1 and so on dxn, gamma n, depending on these points x1 and so on xn, phi on x1 and so on, phi on xn. So these are the kernels we introduced before as simply the functional derivatives of gamma with respect to phis. So gamma n is defined, was defined as a kernel of this gamma, which is simply the nth variation of derivative of gamma with respect to this fields phi on x1, phi on xn. So gamma on phi is a generating functional for vertex functions. Generating functional for vertex for vertex functions. Now, this connection between the 4-point connected Green's functions, say 2-point, let's first make 3 points clear. So graphically, this relation between connected Green's function and vertex function can be expressed by the following drawing. So you have a full Green's function, full propagator, which you can denote as a following blob, a circle, with 3 legs coming out. This would be what I denote by G3 on x1, x2, x3 connected. So full connected Green's function with 3 legs. So in 5-4 theory, we cannot have this situation because we know that in the 5-4 theory, we cannot have diagrams with 3 legs coming out. All odd Green's functions vanish. But in other theories, like for instance, phi cube, you can have such a situation. And so first you start from this 3-point dressed, fully dressed or full Green's functions, if you wish. And then we see that this is a quantity which is here, which is this one. While on the right-hand side of this relation, we have a vertex function gamma, which I denote by means of making this blob shaded. And then it is connected by 3 full propagators, which I denote by these little blobs. These are full propagators, which are nothing else as G2 connected. Yes, and then this relation here is, I mean, this graphical representation is exactly this formula which you see here. I take gamma and I restore the full propagators. I attach to it full propagators, and then I get the connected Green's function. And so you see that other way around, you can say that you obtain gamma by taking the full Green's function, G3, and cutting out or truncating the full propagators. So cutting out these full propagators. And cutting out full propagators leaves me with gamma, which I can consider, which I can interpret as a vertex function, being the sum of all one particle irreducible diagrams or one particle irreducible blocks, which then dressed with the propagators attached to produce back the full Green's function G3. In fact, you can continue this game. You can apply one more, we can apply to this relation one more functional derivative with respect to J, and then you will obtain a relation between the full Green's function, which is a 4-point Green's function, like this. You can obtain a relation of this Green's function with gammas. So gamma 4, the relation will be like this. So you will be attaching now to this gamma 4. The 4 are full propagators. And in addition to that, you might have also such a situation. And also, on the top of that, you will have 2 more blobs with gamma 3. So gamma 3 will appear now. Gamma 3 here. Another gamma 3 here. Gamma 3, gamma 3. Which are reconnected and dressed back by means of full propagators. There will be one more graph. In fact, these graphs like corresponding to S and T and U channels. Like this. And this is again another gamma 3 and one more gamma 3. Okay. So in other words, any Green's function in the theory can be constructed from proper vertices. So these are our vertex functions, so people call them also proper vertices. Proper vertices and dressed propagators. Proper vertices and dressed propagators. So these blobs like this, I'm writing as dressed propagators. Dressed propagators. So proper vertices and dressed propagators make for you all connected Green's functions. The story repeats. If you go to higher point Green's functions, the situation will not change. The situation will be the same. But what is very important, I mean, what is the, how to say, profit of introducing the vertex functions and dressed propagators is the following. That the diagrams, the skeleton diagrams, which you see on the right-hand side of these schematic equations, they are constructed from combining these proper vertices with dressed propagators only as tree-level graphs. So all the graphs which you see here are tree levels, are tree-level graphs. So all, and this is very important, all graphs here are tree-level, or as we call them, they are trees. They do not contain loops. There are no loops. And since a tree diagram is never divergent, if all the vertices, proper vertices, and all the dressed propagators are finite, then there is no any other source of divergence which can appear on the right-hand side. So in other words, this is what is written down here in a way is an approach to represent the quantum field theory, which is encoded in these connected Green's functions on the left-hand side, as a free theory in which only three diagrams are present, therefore, but in which you have a presence of all vertices, of all kind of vertex functions, and the dressed propagators. So vertex functions and dressed propagators make you a kind of free theory in brackets on the right-hand side. So this means that the whole idea of further renormalization of the theory, in other words, of making the theory finite at any given order of perturbation theory, gets shifted to the renormalization of proper vertices and dressed propagators. And these proper vertices, they are nothing else as one particle irreducible imputed endpoint functions. Okay? So you take an endpoint function, you impute all external propagators, you sum up all one particle irreducible graphs, and it gives you the corresponding gamma. It gives you the corresponding gamma. If you are able to renormalize this gamma, that means that you can renormalize your full quantum field theory, because in this way you renormalize all Green's functions of the theory. So these propagators, they are just G2s, and the inverse of them are gammas. Okay, so this is explains the concept of vertex function, vertex functions, their importance for renormalization procedure. And in fact, if you look at the modern literature on renormalization, you will see that in many situations, in many occurrences, people prefer to work with vertex functions and renormalize them rather to directly work with Green's functions. And again, for the reason which I'm explaining here, because once you renormalize all one particle irreducible graphs, which is essentially the same, have the same content as these vertex functions, then you renormalize the whole theory. Okay, I think with this I would like to finish. If you have any questions, I think yes, I will answer.
See, sir. Sir, in the earlier part, I didn't understand why you took delta by delta jx equal to 0. It's earlier part.
Where you say?
Yeah. Here, integral del 3 is wj. This part equal to 0. Why you took this?
That's because on the right-hand side of this expression, there was this delta function. And now I apply to both sides of this expression variational derivative delta delta j. But delta function is just a numerical function. It does not depend on j. So its variation on the right-hand side produce here 0.
Oh, okay.
Right? So on the left-hand side, I vary the first term. This by Leibniz, so I apply Leibniz rule. So first I vary the w. This gives me this term. Nothing happened to this part. Then I do not touch the first part, but I vary the second part, this one. And I do this by using this formula for variation where I replace variation over j by variation over phi. And on the right-hand side, I vary delta function, but delta function is just a numerical function, doesn't depend on j, therefore on the right-hand side, I get 0. And
Yes.
then, I mean, I derive this relation, I derive graphically this relation. But if you continue this process and perform one more variation with respect to j to produce one more leg, then from that functional expression, you will derive this relation here. There will be a gamma 4 appearing and 2 gamma 3s in various combinations with dressed propagators. You can perform this. This is an interesting calculation. You can see how this, all the diagrams on the right-hand side do appear. So in a way, this means that we are decomposing the Green's function into more elementary blocks. We are saying that the more elementary blocks are these vertex functions, which encode only one particle irreducible graphs. As soon as we know all one particle irreducible graphs, then summation of the theory is a summation of tree-level diagrams. Tree-level diagrams constructed from, in a way, Lego, how to say, constructor, where the Lego elements are these gammas. So you have only gammas, and from these gammas, you build up any connected diagram you like. And this, the game of this construction, the way you construct these diagrams, is that you never take loops. You never, all loops, if you wish, are there. They are already inside. They're already summed up. They're already inside these blobs, either in gammas or in these dressed propagators, which are in fact inverse of gammas, of gamma 2s, gamma with index 2. So all the loops are inside these blobs. You see, it's a way to compactly represent the theory to hide all loops, which are the sources of divergences, inside these blobs, and then to have just the tree-level expansions like in a free theory. For this reason, dealing with vertex functions, sometimes people call this field phi on X, they call it classical field. Classical field. But the price, of course, to pay is that very often, I forgot to say that this is gamma on phi, very often is called effective action. Effective action. Yeah, so the original action you start with was an action where you have only phi-4 interaction term, right? So phi-4 interaction term, but with this phi-4 interaction term, you produce all kind of Feynman diagrams, which also include loops and so on. So you have loops. Now, with an effective action, gamma on phi, you have only tree-level diagrams, but the price you pay is that now you have an infinite number of these interaction kernels, gamma on phi. You see, you have gamma n on phi on which the functional depends. And so this effective action now is an action which you have to use to write down all the tree-level graphs, no loops, but all the loops, they are already effectively, in a way, summed up and sit in these gammas. That's why this gamma on phi is called effective action. And the actual utility of this effective action comes from analyzing and investigating the series with spontaneously broken symmetry. This is where this gamma phi effective action is used to compute the effective potential and so on. So there is a whole big story and big theory which is related to this effective action, which is due to Sidney Coleman, this concept.
For that, we need to minimize this effective action, right?
Yeah, exactly, yes, exactly. But this is where it comes from. So I explained to you the origin of this effective action, how it arises, and why it's called effective, because it's effectively summed up, or maybe we did not sum up the loops, but what we have done, we clearly identified their contribution. So in a way, you see, what we managed is to rewrite the whole theory is a tree-level theory. It's like a classical theory, but with infinite number of interaction vertices represented by these gammas. So we have only propagators and vertices, but the number of these vertices is infinite. But we have only tree-level graphs. So all the divergences now are hidden in these gammas. And this is for you in future, if you want to study further this subject, that this is where is the right place to start the discussion of renormalization procedure, how to renormalize gammas and get rid of infinities, because then you renormalize the whole theory. You can be sure that no other infinities appear, because out of this, you use these quantities just to construct tree-level graphs, which do not bring any further divergences to the theory, because simply there are no loops anymore.